Okay, so the next topic is the second pathway. Okay, so here we have still we have high resources, but the recall we don't require too high. Okay, so we can consider another method called the IBF inverted file system. Okay, so again, we use this data set, and now we try to build an inverted file-based solution called inverted file index. Okay, it's a classical way to use like inverted file idea to build your index structure. Okay, so first, okay, there are two steps. First, we have to check partitions about your high-dimensional vector space. And then we will build an inverted file to add a vector to all the inverted files. Okay, so the first step is the channel partition, and we usually use to find a space partition by using some technique like the clustering based, for example, K-means method, or we use the LH based is a hashing method to build your index structure to build your space partitions. Okay, here is an example. You can see we use this data set as our training. Okay, so then we find 1, 2, 3, 4, 5, 6, 7 partitions here. And each partition is represented by using the centroid here. So generally you can use K-means to have this result easily. Okay, so although K-means is take a lot of time. Okay, so you should not use all the 1 billion to build the partition. Maybe you just click a sample, for example, just 1 million data sample for your database to build this to check by using the K-means and find these centroids and the partitions. Okay, so after you build these partitions, then each partition is a region. So it means any data they just located inside these regions, they belong to this partition. And each partition we associate with the inverted file. This here, you can see it's a list. And each bucket we store a data ID, the data point ID. So this structure called the inverted file index. Okay, any problems? Okay then, so this slide shows how we insert the vector here. So given the data point x1, okay, so the x1, then you have to check which partition it locates. If it locates in this partition, you just insert this data ID to this bucket. Okay, so then you can insert the next data point x2. So how to determine which partition it locates? You just compute the vector between all the centroids to find which one has the smallest distance. Okay, so suppose this centroid has the smallest distance to S1. So this means S1 will locate in this region. Then you store S1 ID to this bucket. Okay, any problems? Okay, so it's what we call how to add our data. Okay, the cells, or we call the partitions. Each cells is a partition, and it's focused because Voronoi cells. Okay, so it's a Voronoi cells. Yes. And here, the parameter used to build your inverted file is use the parameters, the number of clusters. Okay, you have to determine how many clusters you are going to use here. Okay, so K-means is to determine how many Ks you are going to use. But it's a try and error. We don't know what size of K is the best. We just try it. But there are some clustering techniques you don't need to determine how many clusters. It will find the best number of clusters by using this algorithm. Okay, later we will, I think if we have time, I can present the technique to you in our clustering lecture. Okay, in the search phase, after you build up your index structure. Okay, so in search, I will give you a query here, and I want to find the nearest vector, Q. Okay, so again, you just search which central is the nearest to the query Q. Okay, so suppose Q is you just compute the distance to all the centroids and find the minimal one. And suppose this one as the minimum, the distance is the smallest. Then the query Q, you just check the inverted file is here. Remember, here we store a set of data ID, so you just check which one is all you can check, all is your candidates. So you have to compute the distance between all the candidates with the query, and then output the smallest one. Okay. Any problems? Okay, so here the search parameters is the number of clusters to inspect. So it means how many clusters you are going to inspect. And in my previous case, I just checked only one, because this one is the closest central. But if you only check one, it's like a greedy search. So we have said the greedy search is usually lead to a bad recall result. Okay, so if you want to increase your accuracy, you should perform the bin search. This means you should inspect more number of clusters, right? So maybe you should check also this one and this one. Maybe you just check the 3 closest centroids as your candidates. Okay, so you can check their inverted files. Again, it can help you to increase your accuracy. Okay, but it means you have to inspect more candidates, so you have to spend more time to do the ranking. So it's a trade-off. Okay, any problems? Okay, 如果你们有问题的话，你可以用中文问，没问题。然后我们英文授课，他是说只要70%的时间用英文讲就好。但是如果你真的听不懂老师讲的那个英文的话，就直接用中文问也可以。好。
Why is it called inverted file?
Inverted file.
Which part is inverted?
Inverted file. Because it's such an architecture, it's called an inverted file. We will not scan. If we want to find which data point is close to our query, okay, if we perform a brute force search, we just check according to the ID. According to the ID from first one, second one, third, we will check in this way. But it's just depend on your luck, right? Okay, so if we can organize this data in this way, this means they are very close together. Because you perform a clustering, the similar data will close together, will aggregate in one file. This here. Okay, so it's what we call inverted. Yeah, this means we will check the clusters, which cluster is close to you first. Then each cluster associate with a file list here. So I think they call such a technique called inverted.
It seems like a hierarchical level.
Hierarchical. Yeah, it's if you mention about hierarchical, actually it can be. We usually means here we can build a hierarchical cluster. Okay, this means your cluster can be like the K-means, you can build the first clusters for your first you can build several levels of clusters. Yes. Later we will introduce a technique called hierarchical clustering. This means first I build 1,000 clusters, and each clusters I build 1,000 subclusters. So I have a hierarchy, right? So in total I will have 1 million clusters. Each subcluster will have a file list here, and in average there are 1,000 data points. So because I have a 1 billion data, right? But if I have in total 1 million subclusters, each subcluster just have in average 1,000 data to be trained. Okay, so it's just use a technique for the hierarchical way to help you, because if you build such a hierarchy, you can check it more efficiently. Okay, any other problems? Okay, then this slide shows how to choose your parameters in this in here. Okay, so the basic idea is, okay, we hope we can check only the 0.0001% of your data set. Means I just want to check just 1,000 candidates in the 1 billion data set. So if I want to achieve this goal, this means, okay, so during the search strategy, I want to check only 1,000 points. So actually, how many clusters I should have? 1 million clusters. So if you build, if you build a partitions containing 1 million clusters, in average, each clusters contain 1,000 data points, right? So I can achieve this goal. Right? But 1 million clusters is very huge, right? It's also a very huge data. You create a very large index structure in here. So if we want to making this practical, okay, so we can build an index on your centroid again. We got it. We have to build another index structure on your centroids. Okay, so standard solutions like this. We can build a graph on the 1 million centroids, and each centroids we can build. Then we use an inverted file to associate with these data points. Okay, so you have two different structures. It's like a hierarchical index structures to manage your 1 billion data. OK， 好，这个意思就是说，你的10亿笔资料，我先建了100万的群中心，100万的群，然后这100万的群太多了，对不对？好，我就建一个 graph， 就刚刚用的 graph 方法，好，那刚好建一个 graph， 然后当你用 graph 去搜寻的时候，你搜寻到那个对应的群中心的时候，好，那你看每个群中心下面不都有1000笔资料点吗？平均来说，那你就去用它来的反向做一个。去做那个搜寻的，看它的概念是这样，所以你建了2层，这样就说这样的概念。Okay, so it's a standard way to process it because of the graph-based structure. Because although it takes a lot of memory, but if your memory size, if you only handle 1 million centroid, it's okay. Just maybe just 50 gigabytes. It's okay for common computers. Okay, so it's okay to build a graph database here, and for your inverted file, it takes a few memories. So it's a very good combine the graph-based structure and the inverted file structure together. It works very good. Okay, so that we can achieve this high performance. Here, this figure shows that this is a comparison required. So if we fix our record to 0.8, and we only need to check, for example, in this method, only check 1,000 data points. Okay, any problems? Alright, so to choose the IVF-based approach, so the advantages for this method it's easy to predict your index size and easy to understand the parameters. The only parameters you have to choose is the number of clusters, right? You just determine how many clusters you want to build your inverted files. Okay, so it's easy to understand and easy to estimate is index size and also because just only one parameter, it's easy to analyze its performance between the index size and also your accuracy, your search time. And also it's easy to implement it. And there are GPU-based solutions for this method. And the disadvantages, okay, so because the recall is not as good as the graph-based search. Okay, so if you want to improve your recall rate, your accuracy want to be improved, you usually need to search more candidates. Okay, it's a problem. The second is quantization. Okay, so because you have to compute so many candidates, you have to spend a lot of time to do the computation. So if you want to reduce the computation time, you can apply the quantization technique. Okay, we will address the quantization technique later. Alright, so if you want to use this method, okay, the best way to recommend to you is use the Facebook face. The face library, okay, just it's very easy to build this structure. Okay, if you want to, so our assistant just show you use the face or the widget to build. Okay, you can choose which one, but I think the face library you can just install on your own computer. Yeah. Right? Widget is more complicated to set up in your client. But it's easy to set up on the cloud. Yeah. But only keep for several days. Yeah, 2 weeks. 2 weeks. Okay. I think Face is a good choice for you. So this is very easy to use. Okay. So let's go to the next track. Okay, so here, if we don't have enough memory, like in our situation, most of us, we don't have enough memory, so we should choose this track. Okay, so then we can check, then we can consider if we want a high recall or not. Okay, but because we don't have enough memory, and you want to include all the data in your memory is impossible. We have to use some vector quantization method to alleviate this problem. Okay, so here are some quantization techniques you can apply in this method. Okay, so we check the face. Okay, in face library, you can use these configurations to do your quantization. Okay, let me explain it later. But generally, you can see here for this parameter setup, you see they use the IVF and the HLSW. They combine the two techniques together. So this is what effective I have mentioned in the previous slide. So you just cluster with 1 million centroid and use the HLSW is a graph-based method to build your index, to index these centroids. Okay, so here, just right here, HLSW to index the 1 million centroid. Okay, but because your memory is not sufficient, so you have to apply some quantization technique to do this. Okay, so the best idea is like this. Okay, so suppose you have this data set, n data set. Okay, so for each data set, for each data is a vector, we want to convert it into a code. Then you just use the code. You see, the first vector convert to this code. The code is very compact compared with your original row vector. Okay, so it's the second vector convert to a second code. The nth vector convert to the nth code. So the reduction in the memory usage can be very significant. Okay, so you see, in your original raw data, suppose you have is your raw data, you need 4 ND bytes to represent n real value vectors using float. The 4 means 4 bytes to represent floating points. Okay, and the n is your number of data, and d is your number of dimensions. So it means if your dimension is 128. And your number of data is 1 billion. So this means you need to, when you have to store the whole raw data in your memory, you need more than 500 gigabytes to store this data. So it's very huge, right? But we don't have such. We only have just 64 gigabytes. So you cannot load all the raw data. Okay. So the idea is we can convert each vector to a shortcode. Okay, so convert all them to a shortcode. The shortcode here, for example, we can use only 32 bits. It's needed 4 bytes, but use 4 bytes to represent, convert this original vector to a 4 bytes code. And then it means you only need 4 gigabytes to store the 1 billion data. Okay, so 4 gigabytes is much small, right? Maybe I think your common computers can handle it. And when you are performing a search, you have to perform a search for the shortcode, perform the computer similarity between the code and the query. Not normal in your raw data. And there are some criteria we want the conversion should achieve. First, the distance between the two codes can be calculated. I can compute the distance between them. And also, the distance can be computed very fast. Okay, it's easy, but because they are short, so the computation can be more efficient when you compute with these two computed in the raw data. So it's okay. And the distance should be approximate to the original distance. So it means when the distance between the two original vectors, after they convert to the shortcode, their distance should be close to the origin. That's the main idea. Okay, O is relative close. And the code should be very small or smallest. Okay, so there are some quantization techniques can be used here. Okay, first use the low precision. It means you should not use the 32 or 64 bits to represent a float. Maybe you just use the 16. Okay, just use 2 bytes to represent a real value. Okay, I think it's a very and it's a general way. Okay, if you can also use 8 bits, just 1 byte to represent a floating point. Okay, but you have to do some compression. It's a common way used. For example, if you have some hardware, or you want to perform the implementation in the transformer, when you perform the attention computations, you can also compress and use a low precision to do the computation. Okay, so very easy and common technique, widely used in many areas. Okay, so the first one. And the second one is called a scalar quantization. Okay, the scalar quantization is like this. Here we will find your minimum, your interval, and the maximum. And we will divide this interval into several parts. Okay, for example, here we divide it 1, 2, 3, 4, 5. Divide it into 5 parts. And each part they have the same width. And we can use this to do the scalar quantization. So this is the basic idea for quantization. Okay. Here is an example. Suppose we divide the interval from 0 to 3 into 6 parts. And then given you a vector here, then for 0.54, I can encode it into 1. For 2.35, I encode it into 5. Okay. This means I just divide each value, each floating point by the 0.5. And the update is, then I can update according here. Okay, any problems? Okay, so it's called it's a scalar quantization. It's also very easy. You just quantize this value to an interval. Okay, also you can use use some locative sensitive hashing method or binary hashing method. Okay, so we will talk about the hashing technique later. And the next one is the product quantization. Okay, here I give you an overview about the product quantization, PQ. Okay, in PQ we will split the data into sub-factors. In this case, I have here the dimension is a 6. So I divide the dimension into 3 parts. The first 2 is the first part, and the next is the second part, and then the third part. And then for each part is a 2-dimensional vector. Right? So I will draw the k-means. Here, the k is said to be 256. Okay, so I have a 256 enclosed on the first part is a 2-dimensional vector space. Okay, so there is here we show is a code book. The code book is the centroid of your first part. And we follow the same way. For our second part, we use the third and the fourth dimension to form our second part dimension. Second part of dimension space. Okay, then perform the k-means again to generate the 256 centroids here. And then this is for the third part. Okay, all of this we call it a code book. Okay, any problems? Alright, so after we build up the code book, okay, then we can start to do the quantization. So first, take the first take the first part here. We check the first code. Okay, so we just compute the distance between your vector and all the centroids here, and to see which one is the smallest. And suppose the second centroid is smallest compared to the vector. Okay, so we can make a calculation here. So your first code is 2, because I have the smallest distance with the second centroid. So here I make a record here. Okay. Next, I compare to the second part. The second part is here. Okay, you can see this two-dimensional vector compared to the second code, and to find which centroid is the smallest. Okay, here the smallest centroid ID is 123. Okay, I just repeat it for the last one, and the find the centroid is 87. Okay, and this method is called product quantization. Okay, so product quantization is actually a general version of the scalar quantization. Scalar quantization is a special case, because scalar quantization only deal with one dimension. But product quantization can process as many dimensions. Okay, so this method actually is very simple and memory efficient, because you already compress a lot. And you can also estimate the distance. When you want to estimate distance, okay, so first, you see, in your original raw data, okay, each value, the floating point is represented by 4 bytes. Okay, but by using the product quantization here, you can just use actually the two vectors, the two-dimensional vectors is compressed to a number. The number is from 0 to 255. Right? So you can use 8 bits to encode it. So each part you can just use one byte to encode it. So if you have 3 parts, you just take 3 bytes to encode it. Rather than it, if in this case you have 6 floating points, and each floating you use 4 bytes. So in total you use how many? 24 bytes, right? But compared to this, only 3 bytes. So the compression ratio is 8 times, right? So it's a lot of saving by using this method. Okay, in the real case, if your dimension is 128 dimensions, and each dimension use 4 bytes to encode it. Okay, actually you will need 512 bytes. Okay, equal to this one, right? 512 bytes to encode this data. But if you divide this data dimension into 8 parts, and each part use 8 bits to do 1 byte. So in total you just use 8 bytes to encode data points. So you can say 64 times storage here by using the original you did, replace it by the product quantization. Okay, any problems?好，那这个就是一个压缩的技术了，这算是就是一个 算是最经典的product configuration 的一个压缩的技术。你看可以看到说原来的资料量啊，从512个 byte， 缩减到只要8个 byte， 压缩率是到了64倍，所以大量的压缩你的资料，就用这种方法来做，这是非常有效率的方法。当然它不太准，你知道压缩它就是 information loss， 那就会算起来就是不准。但是记忆力不够，你就只能这样做。Okay, so when we want to perform the distance estimation, okay, so here is your query, and there is our database vector here. After we perform the product configuration, all the data vector becomes like this. Okay, so here, so you can see we can only have a very compact code stored in our database. So this means we don't need too much memory, right? And the query is here. Note that your query don't need to compress. You don't need to compress your query. A database, all the database vector is compressed, but your query we don't need to compress. Okay, we call such a computation between the two distances called a symmetric distance. It's because your computation between your query and your vector, your query is uncompressed, but your database vector is compressed. So we call it asymmetric. It's not symmetric, it's asymmetric because they are in different states. But how to compute? Okay, so actually you can use some lookup and just use the lookup table to do the computation. The idea is like this. Because you have here, each data is represented by its centroid ID, right? But you can look up the table, look up the codebook. Your codebook will keep the original row vector, the centroid of this code, right? So you can reconstruct it by check out your codebook and to recover it into a two-dimension vector. And the two-dimension vector can compute with the first two dimension in the first part, right? So you can still compute the distance between them. You just check their codebook to reconstruct it, to reconstruct the original code by checking the codebook, and you can recover it to a two-dimensional vector and compute using your query. You just repeat for the second part, for the third part, with the same idea, and the sum all their distance together. You will get an approximate distance. It's not very accurate, but it's approximate. Okay, so we can find it's very efficiently its approximate distance by using the lookup trees. And then we just take this result. Although it's not very accurate, but we still use the result to sort the result and then find our candidates to return the top k nearest neighbors. Okay, so it's how to do the product computation and also how to do the asymmetric distance computation. Here is try to train your codebook to do the product computation, and this is to the PQ product computation to do the encoding, and here this part is do the search. So only tens of lines. It's a complete. It's not pseudo code. It's a complete code. So just 10 lines, tens of lines, you can finish the implementation. Okay, so also you can find it in this library. Alright, let's explain more details about the parameters. You don't need the previous codes. You just use the face library and with this configuration of your parameters. It's very easy. It's called index factory. The index factory is like you just give a different parameters, it will give you the product, the index. The index you want to use. It can generate the model very efficiently. It's like a factory. Okay, so in face, here you can see the parameter used is the OPQ 64128. So it means I use the rotate PQ. It's an optimized PQ. It's an advanced version of PQ. So it's can produce a better product combination. Okay, I use the OPQ here. And the next one is I build the clustering with 1 million centroids and use HNSW graph structure to do the index. And then finally, this parameter setup is to compress your vector into 128 blocks. And each one just use 4 bits to do the compression. Okay, so it's only 4 bits. So in 4 bits means you only have 16 code words as your code book. Okay, it's very small. But why they use only 4 bits? Because some special hardware memory called SIMD based such a memory is only use 4 bits to do the encoding. So that's why they use the 4 bit to generate their code word, and so that they can fit to the special hardware design. And it can be done very fast because of the hardware acceleration. It can be very, very fast. Okay, so it's a special design here. Okay. You just try it, use the face library. You can try it to fit your application. Okay, any problems? Okay, so let's see the ALM search pipeline again. Okay, so before we build our data sets, okay, you have to take several hours to build your index. But in your search, you just take a million seconds to do your candidate selection and scan your candidate here. This is a general idea. But if your memory is not sufficient, so we have to compromise to do a search like this. Here, we will just to use our graph structure to find a set of candidates by code. This means all the data points are compressed. Okay, so if they are compressed, you can fit all in your small memory. Okay, so we compress all the data points here and use the graph structure. But when you compute their distance, they are inaccurate because you only compute based on the by using our product combination and compute the symmetric distance here. Because it's inaccurate, so maybe we have to perform a second round. It's called a re-ranking. Re-ranking is try to compute the true the query with the true vector, not the compressed code. Okay, so we can find the real distance here. Okay, to make your performance more accurate. Okay, so we have the second round called re-ranking. 好，这边我解释一下，就是因为这些点都是压缩过的，因为机体不够，所以你只要压缩。那你压缩完之后呢，你在搜寻的时候，你就是只能用这种非对称的距离去算，它就不准了。那不准，你想要让它更准，那怎么办？就要做第二阶段，做 re-ranking。好，那 re-ranking 的话就是拿真实的没有压缩的资料跟 query 来算，好，那就会准了嘛。好，那就是这样子来去提升它的那个准确度，它就比较耗时。好，那就不像我们记忆体如果够的话，我们就这样做就好了。你这些都没有压缩，你算出来就是正确答案。 哦，那但是记忆体不够，你就只能这样做。哦，先压缩，先在压缩的那个领域去算，算完之后呢，你再把这些候选人，哦，筛选过的候选人，再拿去算它真实的距离。So we have the second phase. It takes more time, but it can improve your accuracy when you don't have enough memory. Oh, it's a trade-off. Okay, any problem? Okay, so here we show the index on the quantized vectors here. Okay, so after you quantize, do the vector product convolutions, all the data, okay, you can encode it into 32 or 64 bytes. Okay, so if you want to store all the 1 billion to your memory, okay, I think this can be stored here. And but because your data is compressed, the accuracy is not as good as before. So here, this figure shows if you perform the product combination to do the take rate, but you don't do the ranking without the ranking. Okay, this means we don't perform the ranking here. We just use the result as your final nearest neighbor, and the accuracy, you see, is not very good. So here is your recall. You see, it's not very good. But if you add the ranking mechanism, okay, it can be improved. But your speed is not as high as without the ranking. Okay. Okay, so generally, if you want to build an index on the top, okay, so for the graph based, okay, so typically you have to choose how many degrees, how many neighbors you have to connect. Okay, so it's the index size, you have to consider how many degrees you want to connect. For IBF, we usually use 1 million centroids and build an index on it. It usually works well. Okay, you can choose which one to build your index. Okay, so next we will talk about the disk ANN. This ANN provides a very good solution if you don't have enough memory. Why? How can you check it? Okay, because it uses the SSD. If your memory is not sufficient, okay, you can store some data in your SSD. Your SSD usually is not as expensive as RAM. Yeah, but its speed can be faster than your hard disk. Right? So they think we can store our index structure and our data on SSD. Usually the SSD may be 1 terabyte or 2 terabytes. It's sufficient, not enough. Okay, so they think this paper published by Microsoft India is a very clever design to handle if your memory is not enough. You can use this way. Okay, in this way, you see your data is too many. Okay, the data set is too big. It's really maybe more than 500 gigabytes. Okay, you cannot store in your memory. You store this part on your SSD. You only store your graph structure in memory. But the graph, you cannot store all the graph structure. You can just store maybe just 1 or 2. Others are still stored in your SSD. When you need it, you just load it in your memory. Okay, so they use this policy to deal with the insufficient memory case. Okay, the general idea is, okay, I put first for 1 billion data, I will run k means. The k is 40, so 40 clusters, and each point we assign to nearest two centroids. 好，就是每一个资料它都会分群，它会分群到最近的两个群中心。好，这跟 K-means 有点不一样。K-means 是每一笔资料都存在于最近的群中间。好，那可是这个会存在最近的两个。Assign each vector to its closest two centroid. So it can because it means your data can exist on two centroids. So its extent is probability to be searched, to be found. OK， 好，它是增加它的可见率，就是this idea. OK， so it means I build 40 clusters. Each clusters I use a graph to build this index structure. Okay, so you can imagine that I have 40 graph structures here, and only one is low in our memory. All the others, your raw data and your other clusters graph structure are put on SSD. Okay, so your memory only store one structure, graph structure, and also you store the compressed data here. The compressed data is use a PQ. Okay, so remember our PQ, we can compress all your 1 billion data. You just spend only 32 gigabytes to do a compression, to do PQ. 就是所有的资料你都做 PQ 了。然后把它放到资料库里，放 memory， 只要32 G 就好，10亿笔只要32 G， 因为它压缩过 ，because they are compressed, so only 32 gigabytes can is sufficient to put the PQ data for 1 billion. Okay, so you put it on your memory here. Okay, so when we are going to do a search, okay, how we do? Okay, first I will read your data and also your neighbors. Also, remember we have a graph structure here. Okay, so all the data, suppose I start from here. Okay, so when I read this point, okay, I can check from the rank to see is compressed data PQ code, right? And then I will find its neighbors, or its neighbors here, here, here. I have 3 neighbors, right? So I will check the 3 neighbors also in my rank to check their distance, to check their PQ code. And when I find they are my neighbors, I find their PQ code, I can compute the distance to the query, right? But it's inaccurate. Okay, then I will go to my SSD. Here is SSD. This part is SSD. So I will find, okay, I have the 3 neighbors. I will check their ID. Okay, from this I check their ID. So check their ID, for example, is data 1, data 2, data 3. Okay, I will find data 1. And also the data 1's neighbor. The data structure is organized like this. Each data ID I will store their neighbors in SSD. So when I check in my rank, and I will also check in SSD to see who will be my neighbors. And all these neighbors I will load in the memory. Okay, to compute, to check here again, to see their PQ code, and I can compute their distance to the query again, and then do a sorting. I just only keep 3 candidates, and only the 3 candidates. Then I will check in SSD to see who will be their next neighbors, and then compute. I will take this neighbors to compute the distance to the query again. So the computation is always performed on the URL and based on their product combination code. Yeah, but each time when I find my candidates, I will go to my memory, SSD memory, to find its next neighbors in the node to repeat this algorithm. And finally, I will converge to find my next neighbor. That's the general idea. Okay. And note that when each data point, when they read their neighbors, they will also, here is a special block. This block keep the original vector. So the original vector, they hope they can make with this design. When I read a block from an SSD, I will not only load their neighbors. I will also the neighbor ID. I will also load the original vector of xi. So that I will take the xi back to the memory. Before in the memory, I only compute the distance on the compressed vector, right? But when I can load the original vector back to the memory, I can compute the real vector distance between the query and the original vector and replace the original distance and make the result better. Okay, so it's a very special, I think a very smart design, so that it can even the computation is mainly on the PQ code, it's on the compressed vector, so the accuracy will be not very good. But with the smart design, it can alleviate this problem. 这段也许你听得比较不懂，因为它图里面做的蛮简单的，这样讲，它大概是这样做，就是在机体里面全都是压缩过的，都是 PQ 做的压缩的。好，所以我有个 query 来的时候，我都是跟这些压缩的这些资料算距离。好，那假设我在这里，我的起点在这里，好，那我就会算出一个我这个起点跟我的 query 的距离，就会算，就是照我上个礼拜介绍的那个 graph base 的搜寻的做法来做。好，那我在算的时候，我会把它的邻居都找出来。它有3个邻居了，从这个起点开始，它有3个邻居，1、2、3。那我这3个邻居呢，我都会去到我的 SSD 去找。好，就是我有，这是第一个点、第二个点、第三个点，那我都可以去找出这3个邻居的他们的那个 PQ code， 也可以算出距离跟 query 距离。好，那同时我可以回到 SSD 里面去把这3个邻居点，他们各自的邻居又是谁？好，因为 graph base 的搜寻，它就是要去找邻居的邻居嘛，慢慢去找到最近的，离 query 最近的那个点。好，所以我就可以用这个方法去找出邻居的邻居到底有谁。那这些邻居，我就可以再去回到那个记忆里面，再去跟我的 query 去算。好，那它有个很聪明的设计呢，就是它因为每次那个 SSD 在读的时候啊，它会去读这一个邻居的编号之外，它还会去读它原始的向量是多少，这是没有压缩的，所以它的一起读起来，它就是特别的设计，它至少每次去读 SSD， 你的读取量多少，它就尽量塞，它把尽量有可能的资料都塞进去，好，所以它把它原始的资料也塞进去。原始资料也一起读回来。那一开始 query 都是跟这些压缩的资料再去做计算，不准。可是当你去读取 SSD 的资料回来的时候，你就读到了原始向量。所以原始向量你到这个地方来，好，你的 query 可以再去算一次。之前是算压缩过的向量的距离，现在是算真实的向量的距离，那就更准了，所以它就可以取代掉上次算的那个距离，就是变得更准确的一个结果。好，这是它一个很聪明的做法。好，大概是这样子。好，就我觉得这个 这个做法就有点繁琐，但是很聪明。Okay, sorry, I just illustrate this in Chinese. But if you want to know the detail, you can check, you can read the paper. Okay, it's very complicated, but very smart idea. Okay, they have their second and third generations. The Microsoft India just published it's because this method is very good to address the memory insufficient problems. So they also publish further generations. Yeah, and they release their code on the web. Okay. Any other problems? Okay, finally, I give you some recent development for this. Okay, there is a paper show a new graph approach. The hierarchical trees are like this. It's a hierarchical arrangement, but the leaves are the HNSW. Okay, it's a very special design. Before we use the internal nodes, let's use the HNSW. Here we use the HNSW to organize your classes. And the leaves are the inverted files, right? But they just reverse it. Leaves are the HNSW. Okay, it's a very special design. And before, I think this is not a smart design because HNSW is very big. Its index size is very big. You have to use a lot of memory to do the storage. Okay, so before I think it's not a very smart design here, but they have a very special, interesting correlation method to alleviate this problem. Okay, so it provide a better build time and a good query performance. Okay, there are some automatic parameter tuning. So remember we say some methods, they are very difficult to tune their parameters. Okay, so there are other papers they propose. It's from the Google. They propose how to find good parameters to optimize your search. Okay, so this is called a filter search. Okay, this filter search is a special search test. This means here I will provide you a database with the image and this metadata. The metadata is in text form, like this. It's on my database. And the query is like this. I will give you an image here, and I also give additional text description. And for example, find the most similar images to this query, and left were taken with a Sony camera in 2017 in Vancouver. I give another conditions as a text prompt to filter out as a filter search. Okay, it's called a filter search. So give an image and also a constraint text description to search your database. And your database will contain the image and the associated metadata. Okay, so this test is called a filter search. And this test is called out of distribution. Okay, what I mentioned here is the challenge, the nearest neighbor search challenges. They propose different checks, different tests. Okay, this is another test called out of distribution queries. Here, the vectors, your database are image embedded, but your query are text. So you know the Y is image database. So your database distribution will be totally different from your text query, right? So it's called out of distribution queries. So here is an example. You can see the performance here. So if you use because your database is image, okay, so if you use the image as your queries, your result is very good. You have a high recall and also very good throughput. But if your queries are text, you see, the record drop a lot from 0.6 drop to 0.25 because the image distribution is totally different from the text. So you have to think how to do the search in the two different distributions. Okay, sometimes we also face this test called streaming data. It means your data will continually update your database. We will always have a new data coming in and some data, old data are deleted. Okay, so you have to consider this problem. Okay, so it is not impractical to update your data set. You update your index structure every day, right? Because you have to take several hours, even several days to update your index structure. So it's impractical. So you should have some clever update strategy to deal with such a streaming data. Okay, so all these are the NIPS challenges. Okay, the full test. Okay, the filter, search, streaming, auto distribution over the unsparse data. Okay, so they want to, because the tutorial they want to promote their challenge, so they just give this slides for advertisement. Okay, that's all. Okay, I put the slides on my website, so you can download it from my website. Okay, thank you. So, okay, I think it's time up. Okay, see you. And next week we will talk about how to do a hash, how to find a similar set by using some famous LSH or some hash techniques.